Thank you. Hello, everyone. I'm Agnieszka Herman. I'm from the Institute of Oceanology of the Polish Academy of Sciences. And before I begin, I would like to thank two people who are not here, unfortunately. It's Hayley Shen and Nico Gray. This is also part of my answer to the question what has changed in the way I see sea ice in the past 5 years, because the very long discussions I had with Nico during the program in 2017 really changed how I look at sea ice as a very particular, very complex example of a granular material. So it helped me to see it all in a larger context. And Hayley, among all people I know, I think she's the one who always asks the best questions, so which makes you learn a lot when you try to answer them. As the title suggests, I'm going to speak about the marginal ice zone, but in fact the results that I'm going to show are relevant rather for a certain type of the ice cover rather than location. So it's not necessarily about the MIZ. It might be a different place, but the ice has to be fragmented, composed of individual ice flows which interact with each other and which have a wide range of sizes. And an example of such a location other than the MIZ might be ice flowing through straits, channels, or other basins that have limited width. So here you can see an example of a typical sea ice situation in the Nares Strait in spring, when those very large ice flows are trying to make their way through the strait, and some of them break in the process, as we can see. So their sizes are comparable with the width of the strait. And there are a lot of very small ice flows as well. So the first feature of that sea ice type is very high polydispersity, which simply is a term which describes the heterogeneity of sizes or masses or densities in a granular material. And there are many measures of polydispersity. One of the simplest one is the so-called size span, which is simply a number between 0 and 1, depending on the minimum and maximum diameters or other measures of size that we find in a certain granular material. In the case of sea ice, in many cases, we are close to 1, which is actually outside of the typical range of polydispersities that are analyzed in research on granular materials, which means that we can learn something new about granular materials in general by studying sea ice where we are in this regime of extreme polydispersity. And another aspect related to flow size is that they are comparable with, let's call it system size. In this case, the system might be the width. System size might be the width of the strait, or Veronique yesterday talked about flows filling an ice lead. It might be also a single grid cell of a numerical model. And this is related to the fact that averaging of flow level variables is not trivial. When we look at this image, even the basic variable characterizing the ice cover, which is ice concentration, is really hard to define here. When we imagine we would like to model this situation with a continuum model, we would need a dense mesh to reproduce the geometry of the strait, of course, and then there are ice flows which are with extent covering a lot of meshes of that model. So when we move to the MIZ, here's again a random example. It's a matter of definition what we call the MIZ here, of course. It is a region east of Greenland, again in spring, and actually everywhere we have ice which is which is a granular material. So we can look closer at those three regions here at higher resolution data. So in that outer part, in the background, with those eddies and everything, when we have high resolution images, we can see that the ice is composed of very small ice flows, probably broken by waves. And the size distribution is actually quite narrow here, although we have those single larger flows in between. And then when we go deeper into the ice cover, we have larger average flow size and also larger size span. And finally, that large blue area here. These are also flows that move independently relative to each other when we analyze a series of images. So it is a granular material, although in this case the sizes of ice flows are tens of kilometers or even larger. So some questions appear, which were also mentioned in several talks on previous days. Which flow level processes are relevant at larger scales? Are they captured by the models that are available right now? If not, can they be taken into account, and how to do that? And also, how far can we go with continuum models, in the sense that how high resolution of continuum models is meaningful, considering the fact that we are violating that basic assumption underlying our models, that there are a lot of ice flows in a single grid cell. And there is a theoretical aspect to that, and also a practical one, because already now many models do violate that assumption, of course, and they work quite well. The same problem is known from other type of models, like spectral wave models, which are based on the assumption that the grid has to be large compared to the wavelength, and they are successfully applied in coastal region at very high resolutions. So it often works in practice, but the question is, does it always work, and what are the problems that we might encounter? So today I will talk about problems related to those questions in the context of sea ice dynamics. And the idea is that we can apply discrete element models in relatively simple configurations, so without trying to run them at larger scales. I'm actually not a fan of doing that. I know that there are some people in this room that would disagree with that, but it is a subject for another talk, I think. What I'm convinced of is that DEMs are a very good tool that can be run over a very large number of configurations, relatively simple ones, and the results can help us to formulate parameterizations for continuum models. So as I said, in this talk I will try to show some examples of how we can use DEMs to try to learn something about how polydispersity influences the strain-stress relationship in sea ice, and part of those results can be found in that paper here. This is the special issue on the marginal ice zone that appeared a few days ago. So before I move to the DEM results, just a very quick overview of the state of affairs. I'm in a good situation that a lot has been said yesterday about the viscous plastic rheology and similar rheology, so I don't think there is a need to repeat that. I will just say a few words about the collisional rheology, which contrary to the viscous plastic ones, treats sea ice as a granular material. More precisely, it treats sea ice as a granular gas with high restitution coefficient. This is a crucial assumption in that rheology. And this is actually not true for real sea ice. There are observations from the lab and from the field that show very low values actually of the restitution coefficient. But this assumption justifies the remaining ones in that rheology. And they altogether mean that this collisional regime is limited to a very narrow range of conditions in terms of ice concentration, because on the one hand we have to have the ice concentration high enough to sustain those random collisions between ice flows. But on the other hand, the ice concentration cannot be too high because we disregard all frictional interactions between ice flows. So in fact, there is, it can be seen in DM simulations very well. There is really extremely narrow range of ice concentrations that roughly corresponds to that regime. So the overall picture is that we have that collisional rheology, which is relevant in a narrow zone close to the ice edge, and it is flow size dependent. And then the second rheology used in a given model is supposed to handle all other situations, and then there is no flow size dependence anymore. And what I'm going to show today is like a continuation of what Veronique said yesterday, that we have a lot of situations where none of those two really does what we would like it to do. So this is one thing, and another is quite basic, quite fundamental, and it is related to how we compute stress in granular materials. What you can see here are expressions that can be found in a lot of textbooks and manuals of GM code and so on. And they are valid for materials with low polydispersity. And there are several alternative formulations of stress, which are not equivalent to each other. And in most cases, it doesn't really matter in practice. But when we move to highly polydispersed materials and complicated flow geometries and so on, it does matter. So once more, these are the stress definitions valid for spherical or in 2D circular grains in simple geometries and so on. That's one problem. We often simply do not know how to compute some of those variables, like the velocity, the amplitude of the velocity fluctuations, when we have several orders of magnitudes of ice flow sizes. And also, what we understand about the physics of granular materials can be divided into three regimes, three types of granular flow. At one extreme, we have compact, slowly sheared flows, which are well described and relatively well understood. The other extreme are rapidly sheared flows, those that can be described by the kinetic theory of granular gases. So those two papers define stress in those granular materials, and they arrive at slightly different final formulae for stress. And then there is this middle case where both frictional and collisional stresses are important, which has the most interesting dynamics and most difficult one to simulate, to describe theoretically, and so on. And I would argue that in CS we are often in this place here in the middle. This is the situation when we have a lot of interesting processes at intermediate scales, force networks and force chains and jamming phenomena and so on. And the size of grains or ice flows in our case relative to the size of the domain, it always plays a very important role. So now to the DEM. As I mentioned, these are very simple simulations repeated a lot of times. The goal was to analyze how the polydispersity, so the properties of the flow size distribution, influence the response of a sample of such material to the shear deformation. So we have the flow size distribution or grain size distribution with two parameters. It's a tapered power law. The alpha is the exponent, beta is in meters, and it decides on the onset of that exponential tail. So we have a very simple expression for the area-weighted mean flow diameter in this case. This is important for the mu of I rheology that I will be talking about in a minute. And at the bottom, just a few examples of how those materials look like for two different values of beta. These are just small fragments of the whole model domain. So in the combination of alpha and beta that gives us those largest flows, the single largest one occupies like 1/4 of the total of the domain. So I didn't try to go farther. So we have two varied parameters that describe the FSD, and then we have two additional ones which describe the pressure acting on that material and the shear stress. They are selected so that they correspond roughly to the pressure that we might find 1, 10, and 100 kilometers from the ice edge, assuming a moderate wind blowing towards the ice. And first, a cartoon. What is going on here? If the grains are small, this is a very well studied and understood case, so there's nothing new to find here. We expect a linear velocity profile, and it is also easy to compute the mean velocity and the fluctuating part. But when we add very large objects to that flow, it is clear that something has to change, because as long as they don't break and they move as rigid bodies, so the flow around them has to, on average, has to have roughly the same velocity. It doesn't matter if we are at the lower or upper part of that large grain. So quite obvious part of the result is that when the flow size increases or the FSD becomes wider, we move from that approximately linear velocity profile towards less regular ones, and also the value of that velocity changes very substantially. This is what is expected, of course. So with the same shear stress, we obtain very different deformation rates just by changing the flow size distribution. And this is not the collisional regime. This is the high concentration regime. We can analyze the same thing for larger number of cases and a lot of pressures and so on. The conclusion is the same. for a given deformation rate, we have very different pressures in the material or vice versa. And this is related to what is going on at the grain scale. I know those figures are not very clear, but that's the point, especially in the case of the right one, because there is so much variability in the instantaneous velocities of those small grains that it is hard to plot that. So in a way that would make everything visible here. So that's one thing. Those small grains have to flow around those large ones for the whole material to deform. And we also have orders of magnitude differences in the pressure acting on those grains, individual grains. So the bulk pressure is really non-obvious result of all those microscopic processes that are going on. And the most relevant, I think, part of the results is related to the rheology. The mu of I rheology was mentioned yesterday by Veronique and in some other talk as well. Sometimes it's called mu of I, phi of I. This is the rheology that postulates, as the name suggests, that the two bulk properties of the flow, granular flow, the friction coefficient and the packing fraction, so ice concentration for us, are functions of just one non-dimensional number, which is the inertial number. It depends on the grain size, deformation rate, density, and pressure. And this hypothesis is based on a scaling analysis of governing equations, so it has theoretical background, but all the rest about this rheology is experimental. So there are a lot of papers on the mu of I rheology studying different geometries of granular flows and different types of materials, cohesive ones or dry ones or wet powders or whatever. And all those studies arrive at different formulae for the mu of I curve. So this is just the formula which I think is used most often. I will just come back to that in a minute. Just a side note, the form of that relationship might be very different. Sometimes it's very complicated, non-monotonic. This is example from a paper studying cohesive materials. So the mu of I rheology seems to be still valid, but it has a completely different relationship between the mu of I and phi of I. So back to our results. Each of those colorful points here is one simulation with different flow size distribution or different external pressure and different shear stresses. And the fit, which is shown here, is the fit to this formula. So we move from very low to high bulk friction coefficient with increasing inertial number, and the fit is not perfect, of course, but it's actually better than I expected it to be. All those clear outliers are the cases with the highest largest ice flows. So at some point it doesn't work anymore, but still we can see that in many cases we are in this region here where the bulk friction coefficient changes very strongly, which means that by changing the size of ice flows, like breaking large flows into smaller ones and so on, should lead to a change of the bulk friction coefficient of that that CI. And before I finish, just one example, what are the consequences of that? These are velocity profiles through an idealized marginal ice zone. So here is the ice edge, here is the distance. Deep into the ice, 1 is the free drift velocity at the ice edge. And I computed the velocity profile from using the default parameters of the Hibbeler's rheology, which is this dashed line, and then 3 other ones for different values of beta, so different widths of the flow size distribution. And so as we can see, the width of that zone close to the ice edge where we observe high drift velocities is very sensitive to that change. So I did not attempt to calibrate those values to any real data, but it seems that it really has a very strong influence on how the ice responds to shear stress. So I think that this is the most important conclusion from that the FSD is very important for rheology, not only in the collisional regime, but also in at high ice concentrations in densely packed ice, which undergoes shear deformation. So that's all. Thank you very much.
Thank you, Agnieszka. So, hands up already.
Thanks. When you say, like in your experiment, like you said, the simple shear flow, you said for the same shear stress. Do you mean the same top plate velocity, or you?
No. So I prescribed the stress, not the velocity, okay. Because I wanted to capture also those cases with extremely slow quasi-static cases.
And if you keep the FSD constant, but you rearrange the flow differently, are the results very sensitive to like a random permutation of like the same flow size distribution?
For the cases with largest flows, I tested several runs because yes, the results are sensitive, and there are some arrangements of ice flows that lead to sudden stops of the flow, and then it's on again. So I didn't show that, but with very large ice flows, the variance of the velocity, so of the shear rate, is very high actually. So it reaches a stationary state, but the fluctuations are very high.
So this is the mu high is a nonlinear viscous model. So there's no plastic transition that you observed in the experiments, like when the flow stops, then it's the viscosity then. And I
think I didn't kind of reach.
So it's always a continuous flow that you have.
Yes. So in all cases, the long time average shear rate was different from 0, if that's what you're asking.
Yeah. And next slide, you compared with the Hibbeler, like the linear viscous. You said it was coming from Hibbeler values, no? Or I missed that.
I used some parameters that I found in the textbook by Mattile Parenta. So
okay.
Of course, with different values, you will have different profiles here.
Okay.
That's clear, but there is no dependence on flow size. That's what I wanted to show with this figure.
Thanks.
Okay, thank you. So if you've got any more questions, please discuss them over coffee. Oh, you. Okay.
No. I don't want to have any more. Oh, I do have questions, but I won't ask them now. Okay. As you can probably tell, we're running a bit over time. Okay, we're running about 20 minutes late. So what I suggest is that we try to rescue 10 minutes from our coffee break. So we return here at 11:40 rather than 11:30. And if we possibly eat 10 minutes out of our lunch as well, unless the subsequent speakers are quite fast. So if we can come back here at 11:40, please, promptly, because otherwise we're going to be more